Welcome back. In today's video, we'll be looking into an important concept in TypeScript, generics and type inference. Understanding these concepts is crucial for writing clean, reusable, and type-safe code. Stay tuned until the end for a couple of best practices for using generics in TypeScript. So, let's get started. Before we delve into generics, let's quickly recap what types are. In TypeScript, types help us define the shape and behavior of our variables, functions, and objects. They provide a way to catch errors early and make our code more robust. Generics take this concept one step further. They allow us to write code that can work with different types without sacrificing type safety. In other words, generics enable us to create reusable and flexible code that adapts to different data types. To use generics, we simply add a type parameter inside angle brackets after the name of a function, interface, or class. This type parameter represents a placeholder for a specific type that will be provided when the code is used. Let's take a look at a simple example. Imagine we have a function called identity that takes in an argument and returns the same argument. We can make this function generic by adding a type parameter, conventionally represented as t. Here, t can be any type, and TypeScript will infer the actual type based on the argument provided during the function call. This is known as type inference. Let's look at an example use case for using generics. In this example, we define a generic function print value with a type parameter t. The t represents a placeholder for the type of the argument that will be passed to the function. The function print value logs the argument to the console. To use the generic function, we call it and provide the type argument within angle brackets. In the example, we call print value with three different types: number, string, and boolean. TypeScript infers the type based on the argument provided, but we can also explicitly specify the type by including it within angle brackets. This is useful when type inference is not possible or when we want to be explicit about the types. Generics allow us to write flexible and reusable code that adapts to different data types. We can use generics with functions, interfaces, and classes to create more generic and type-safe code. Type inference is TypeScript's ability to automatically determine the types of variables based on their usage. It saves us from explicitly specifying the types all the time, making our code more concise and readable. Let's see an example. In this example, we define an array logger class with a generic type parameter t. The class has an internal array of type t. The constructor initializes the array, and the logArray method takes in an array of type t and logs it to the console. We create instances of the array logger class with different types number, string, and boolean, and then call the logArray method with arrays of corresponding types. The array logger class demonstrates how generics allow us to create reusable code that can work with different data types. In this case, it allows us to log arrays of various element types without duplicating code. Generics can also be used in more advanced scenarios, such as constraining types with the extends keyword. In this example, we have an interface called printable that defines a print method. Then, we have two classes, book and magazine, that implement the printable interface. The printItems function is a generic function that takes in an array of type t, where t extends printable. It iterates over the array and calls the print method on each item. Finally, we create an array items that contains instances of book and magazine objects, and we pass this array to the printItems function. By using the extends keyword in the generic type parameter, we ensure that only objects that implement the printable interface can be passed to the printItems function. This provides type safety and allows us to work with a specific set of objects. Additionally, TypeScript provides built-in generic types like partial and read-only that further enhance our ability to work with different data structures. In this example, we start by defining an interface called user with properties for name, age, and email. We then use the partial user type to create a partial user object. The partial t utility type allows us to make all properties of t optional, creating a new type with the same properties as t, but each property can be undefined or omitted. In this case, we only provide the name property while leaving out age and email. Next, We use the read-only array number type to create an immutable array named read-only array. The read-only T utility type creates a new type where all properties of T are made read-only, preventing modification of the properties. In this case, we have an array of numbers, and we can access its elements but cannot modify the array itself. Finally, we demonstrate accessing elements from the read-only array, but if we try to push a new value or modify an existing element, TypeScript will throw an error because the array is read-only. These examples showcase how the partial and read-only utility types in TypeScript enhance our ability to work with different data structures by providing flexibility in making properties optional and enforcing immutability when necessary. By understanding and using generics effectively, you can write more flexible and reusable code. Here are a couple best practices for using generics in TypeScript. Be explicit with type annotations. When working with generics, it's a best practice to explicitly annotate the types wherever possible. This helps improve code readability and provides clarity to other developers who might be working on the codebase. By explicitly stating the expected types, it becomes easier to understand the intended behavior of generic functions or classes. Use constraints to ensure type safety. Generics allow us to work with a wide range of types, but it's important to use constraints to ensure type safety. By using the extends keyword, you can restrict the generic type to a specific set of types or interfaces. This helps prevent potential type errors and provides better static type checking. Using constraints also enhances code documentation by explicitly defining the requirements for the generic type. Here's an example that demonstrates both best practices. In this example, the merge arrays function merges two arrays of the same type. The generic type parameter T is constrained to be an array type using extends array any. By explicitly annotating the types of the input arrays number and string and applying the constraints, we ensure that the function works correctly and provides type safety. By following these best practices, you can write more robust and maintainable code when using generics in TypeScript. If you found this video helpful, please like, share, and subscribe to our channel for more awesome content on programming for beginners. If you have any questions or would like to suggest topics for future videos, feel free to leave them in the comments below. Thanks for watching, and happy coding!